In this video, we're going to continue to solve for statically determinate structures. All the problems in this video will assume counterclockwise as positive, left to right as positive for horizontal components, and upwards as positive for vertical components. For this problem, we have to determine the horizontal and vertical components of reaction at A, B, and D, assuming the frame is pin connected at A, B, and D, and there is a fixed connection at joint C. I've already drawn the free body diagram for member AB. Here we have 2 point loads, one at B and another concentrated load at 8 feet below point B, and we have both horizontal and vertical components at point A and B. To solve this problem, let's take a moment about the point B. So we can have sum of forces and moment B equals to 0. Our point first load we encounter is 12 pounds and it's 8 feet away. Second, we encounter counterclockwise horizontal component at A and it's 20 feet away, all equals to 0. Solving for AX, we get negative 4.8 pounds. Looking at the structure, we can see that there isn't any other horizontal component or force acting on the structure. Therefore, we can sum the forces in the X direction to find the value of Bx. We're going to have positive 6 pounds and positive 12 pounds. We're going to have negative horizontal component at A, 4.8 pounds, and negative horizontal component at B, all equals to 0. Solving for Bx, we get 13.2 pounds as a solution. Looking at this free body diagram, we can't solve for any other reaction until we solve for our next member, which is BD. Let's draw the free body diagram for BD. BD has a uniform load in both rectangular and triangular shape. Let's solve for our rectangular load first to convert it into concentrated load. It's going to be 2 pounds per foot times 6 foot equals to 12 foot, and it's going to be halfway through, so therefore it's going to be 3 feet away from B. Next we have a triangular load, and it's area of the triangle, so it's 0.5 times 2 times 6, and this is 6 pounds, and this is going to be 2/3 away, distance away from point C. Therefore it's going to be 4 feet away. And of course we have to remember we're going to have horizontal and vertical component at B and D because it's pin connection. Now let's take a moment about the point D. First load we encounter is counterclockwise 6 pounds and it's 4 feet away from D. Second is 12 and it's counterclockwise as well, and it's 9 feet away. Then we have horizontal component of the B, that's clockwise, so negative 13.2 times 12 feet, and then we have vertical component of B, which is BY, and it's 12 feet away, and it's counterclockwise, therefore positive, all equals to 0. Solving for BY, we get 2.2 pounds as a solution. Now we can sum the forces in the X direction in order to find the value for our horizontal component at D. So we only have one force other than horizontal component at D, and that's Bx. So our Bx is positive 13.2 pounds. Then we have negative Dx, all equals to 0. Solving for Dx, we get 13.2 as our solution. Now let's sum the forces in Y direction in order to find our vertical reaction at dy. So we're going to have negative 2.2 pounds, negative 12 pound, negative 6 pound, and then the positive horizontal component at d, all equals to 0. Solving for dy, we get 20.2 pounds as our solution. We have found all our values except for our section AB, and we still need missing vertical component for pin connection A. So it's going to be sum the forces in Y direction. So we have BY, which is negative, and then we have a solution as a positive BY 2.2, and then we have positive AY, all equals to 0. Solving for AY, we get Our solution has 2.2 pounds. For this problem, the bridge frame consists of 3 segments, which can be considered pinned at A, D, and E, rockers ported at C and F, and rollers ported at B. We have to determine the horizontal and vertical components of reaction at all these ports due to loading. To solve this problem, first of all, we need to segment this structure, and I've drawn a free-body diagram for our first segment, ABC. Here, point A has 2 components, horizontal and vertical, and then our distributed load, I've converted it already into a concentrated load by multiplying our 4 pounds with the total distance of the distributed load, that's 10 feet, from the to be 40 pounds. Then we have a vertical component reaction at B and C. Now we can take movement about the point A. We encounter our first clockwise reaction, 40 pounds, and it's 5 feet away. Then we have a vertical component at B, and it's counterclockwise, so positive, and it's 10 feet away. And then we have counterclockwise vertical reaction at C, 4 feet away, all equals to 0. Simplifying this equation, we get 10 by plus 4 cy equals to 200. Now looking at this structure, we can't really solve for anything else unless we go over to the next section and see if we could solve some reactions. Let's draw a free body diagram for section BD. Section BD has vertical reaction at B, and we have a concentrated load of 30 pounds, and it's 10 feet away from D, and D has both horizontal and vertical components. Now let's take moment about the point A. D, we have our concentrated load 10 feet away from our D, and it's counterclockwise, and we have counterclockwise By, and it's 18 feet away, all equals to 0. Solving for By, we get our By is negative 16.67 pounds. Next, we can sum the forces in y direction to find the value for our vertical component at D. It's going to be negative 30 pounds. Negative and negative becomes positive 16.67. And then we have our positive dy reaction, all equals to 0. Solving for dy, we get a solution as 13.33 pounds. Now we can go back to our section ABC and plug the value of by into our equation. I'm going to name it 1. So subbing the value of vertical component at B into our equation 1, we get 10 times negative 16.67 pounds plus 4 cy equals to 200. Solving for the vertical component at C, we get 91.67 pounds as our solution for vertical component at C. Now we can sum the forces in the y direction to find the value for our vertical component at A. So it's going to be simply cy is 91.67 plus our by, which is positive, and our value for by is negative 16.67. And then we have our positive vertical component 8 plus negative 40 pounds for our concentrated load, all equals to 0. Solving for AY, we get negative 35.0 pounds. We have all the reaction forces except for reactions for our section DEF. Let's draw the free body diagram. We have horizontal and vertical reaction at D. Then we have a point load. Our concentrated load is 10 pounds, 5 feet away from E. And we have both horizontal and vertical component at E. And finally, we have a vertical component at F because of the roller support. Now let's take the moment about the point E. So we have counterclockwise 10 pounds, and it's 5 feet away. We have counterclockwise dy, which we just found to be 13.33, and it's 10 feet away. Then we have clockwise vertical component F, and it's 4 feet away, all equals to 0. Solving for Fy, we get 45.83 pounds. Now we can sum the forces in y direction to find the value for our vertical component at E, which is going to be negative 10, take away 30.33 for our dy, and a positive 45.83 pounds for our vertical component at F. And then we have negative vertical component at E. All equals to 0. So for EY we get 22.5 pounds. Now our horizontal components will be all equal to 0. Reason being there is no external force that is exerting force on this structure that is horizontal. Therefore, everything is 0 pounds. For our next problem, we have to determine the horizontal and vertical reactions at connection A and C of the cable frame. Assume that A, B, and C are pin connections. The purlin loads such as D and E are applied perpendicular to the central line of each girder. Okay. To solve this problem, first of all, let's find the horizontal and vertical reactions for purlin load. To find the horizontal load for our concentrated load at D, we need to times the 600 pounds with the angle, which we can simply find by taking tan of 5 divided by 12. Comes up to be 22.62 degrees. Now we know that theta is going to be this area here, and our point loads will be drawn in such manner. Therefore, to find our horizontal load, we need to multiply our 600 pounds with sine 22.62 degrees, and our horizontal reaction is going to be 137.7 pounds. Similarly, we can find our vertical component by multiplying 600 with cos 22.62, and this comes up to be 553.85 pounds. Now we can find our vertical component for point E, and it's going to be 400 pounds times cos 22.62. It's the same angle because the whole structure is symmetrical, and vertical component is 369.23 pounds, and our horizontal component for point E is going to be 400 times sine 22.2, and it's come to be 153.84. Now we can take moment at point C, but before we do that, let's find this concentrated load here for this distributed structure. It's going to be 120 times 10 pounds, so it's going to be 1200 pounds. Now we can take the moment about the point C to find the value for our point vertical load at A. So the first load we encounter from C is at G, so it's going to be our horizontal edge counterclockwise. It's going to be 230.77 times 12.5 feet, because this vector at G is halfway between the distance from top of this pier to the top of this roof. Now we can have counterclockwise for our vertical component at G, and it's 6 feet away. Then comes our point F. It's going to be counterclockwise as well. And it's 153.84 times 12.5 plus 369.23 and 12 feet away. Now we have clockwise for our point E. So it's going to be for horizontal negative 153.84 times 12.5, and then clockwise for our vertical at E. So 369.23 times 12 feet. Similarly, we have counterclockwise for our horizontal at D. So it's going to be 230 times. Oh, another thing I just noticed while doing it, our vertical distance, our horizontal distance from point C for E and F is actually 15 feet. Now we are going at point D, so our horizontal is 12.5 feet away, and our vertical is counterclockwise, so positive 553.85, and it's 18 feet away. Now our columns. Column A has 800 pound load, and it's counterclockwise, and it's 24 feet away. And then we have our concentrated load for our uniform distributed load. It's 1200 pounds, and it's clockwise, and it's 5 feet away from point C in the vertical direction. And finally we have our vertical reaction at A, and it's 24 feet away, all equals to 0. Solving for AY. AY comes up to be negative or positive 1473.08 pounds. Now we can sum the forces in y direction to find the value for a vertical component at C, which is simply going to be AY, which is 1473.08. Just assuming them as such. And then positive CY, and we're going to have 2 times our 533.85 because we have G and D, and then 2 times our vertical reaction force at E and F, and it's going to be 369.23, and both of these are negative because they're pointing downwards, all equals to 0. Solving for CY. And another thing I did not include here are the 800 pounds here on the beams. So negative 200 times 800, all equals to 0. And now solving for CY, we get our solution as 1973.08 pounds. Now we have our CY, we have our AY, and we still need horizontal reactions at A and C. To solve for our horizontal reactions, we need to section this frame. Doesn't matter which one, either AB or BC. I'm going to take BC. Let's draw the free body diagram for BC. That's going to look something like this. Here we have horizontal vertical reaction for B. Then we have our horizontal vertical reaction from F, and then we have horizontal and vertical reaction from G, and we have a vertical reaction here from this from the concentrated load of 800 pounds. Finally, we have horizontal and vertical reaction at C. And we have found the value of CY to be 1973.08 pounds. For our vertical reaction and horizontal reaction at G, it's 230.77, and vertical has 553.85. For our F, it's going to be 369.23 and 153.84 for our vertical at F. Alright, to solve for our horizontal reaction at C, let's take a moment about the point P. So the very first point load we encounter is D, which is going to be for our horizontal, it's going counterclockwise, so negative 230.77 times it's 2.5 feet away from B, and then our vertical is going clockwise as well, and it's 553.83, and it's 6 feet away. Then we have our counterclockwise, clockwise 800 pound concentrated load, and it's 12 feet away. And finally we have horizontal component of C, it's 15 feet away, and counterclockwise our vertical component of CY, and it's 12 feet away, all equals to 0. Solving for CX. we get value for our vertical component C as 678.47 pounds. To get the value for a horizontal direction at A, we can simply take the whole structure again, so whole structure, and sum the forces in x direction. Looking at our diagram, we know that our D and E, F, and G all will cancel each other out. So the only directions we are left with is 1200 pounds, which is positive, and CX, which is negative, and our value is positive 678.47, and our positive horizontal direction at A all equal to 0. Solving for AX, we get our solution as 521.53 pounds.